Alright, now let's get into hydrohalogenation of ethers. In case of hydrohalogenation of ether, always keep one thing in mind, that HI is more reactive than HBr than HCl. If we react ether with HX, we end up with, now this is symmetric, so both R gets hold of X forming Rx and water. So two molecules of HX satisfying two alkyl groups to give 2 Rx, and 2 H and 1 oxygen forms water. Very simple in case of symmetric ethers. Now let us check out in terms of non-symmetric ethers. These are all unsymmetric ethers. Alright. Now here we have smaller group, lower alkyl group. Here we have got higher alkyl group, ether. Now when we treat it with hot concentrated HI, what we end up with is CH3I and C2H5OH. Alright. Now I call it as Lali. Why do I call it as Lali? Because it is L stands for lower, Al stands for alkyl iodide. Just to keep in mind, I would explain you later how it would be easy for you to follow these abbreviations that I have made for these three reactions. Alright, now the thing that you have got to keep in mind is it's SN2 mechanism, and it's SN2 mechanism, that's why iodine goes to lower alkyl group, which is least substituted. Alright, so that's about when we have lower alkyl and higher alkyl ethers. Alright, now let us talk in terms of tertiary alkyl and primary alkyl ether. Alright, I call it as Tali. Why? Because T stands for tertiary alkyl iodide. So we find that iodine goes to tertiary alkyl group, whereas H part goes to CH3O, to methoxy group, that is linear alkyl group. Alright, so this was Lali, lower alkyl iodide. This is Tali, which is tertiary alkyl iodide. Now comes, and this also is going to SN1 mechanism. Why SN1 mechanism? Because in case of SN1 mechanism, we are quite conversant with this carb cation. Now here CH3, 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 C. So when it goes, it takes oxygen with it, C plus. So we get this carb cation, tertiary carb cation. Now it's one of the most stable. Why? Because CH3 is one of the best EDG, electron donating groups, so it's quite stable, and owing to which iodine goes to this tertiary carb cation rather than to primary alkyl. Alright, okay, explained. So this was SN2, this is SN1. Now again we come to alkyl aryl ether. Alright, in case of alkyl aryl ether, where does I call it as Ali? Yes, right, Al is alkyl, so iodine goes to alkyl group. So iodine goes to alkyl group, and this is phenol. Okay, so what we end up with is phenol and iodine going here, I going here, H going here, H going here, giving you phenol. And why phenol? Now see, we know phenol. Now once if you take this out here, phenoxide, we know phenoxide is negative. Alright, so it is Lewis base, phenoxide. So owing to which I want negative, negative, I is also electronegative, and O minus is also electronegative, phenoxide. So I would prefer to go to CH3. Alright, another theory that we can apply is that least hindered, so iodine goes to this. All right, two theories. So least hindered, so iodine prefers to go to this. Then phenoxide is negative, so I would repel phenoxide. All right, so keep lale tali ale in mind. That would help you to not to get confused with HI reactions, hot concentrated, with varieties of ethers. Again I repeat, lale is lower alkyl iodide, tale is tertiary alkyl iodide, and ale is alkyl iodide. Alright, so I have talked about where the iodine goes in these abbreviations. Alright, I hope you find it quite comfortable. I again repeat, see how interesting it becomes. The chemistry becomes very interesting when you try to do it via flow sheet method. Alright, okay.